What's up, you pussy-ass pussies? I don't know why my skin looks like that. I look fucking disgusting. Alright, anyways, let's get into it. Been a while since I've done one of these. Doing some waves. Waves. Let's go. Alright. Now, I was supposed to be learning the SQR3 study method. But for now, I'm just going to continue taking notes. Alrighty then. Ah. 10th of the 9th. Cool beats. I never actually set waves last year. I actually did physics last year, but never set waves. Let's set this timer, this Pomodoro, or however the fuck you say it, timer. Ooh. Cool beans. Let's go. So I have 25 minutes on, 5 minutes off, 25 minutes on. Then that'll be my study for the day. Waiting for my chemistry teacher to mark my internal. Then we'll start on with externals. And I'll start using Anki and using some flashcards to study. Using SQR3. Survey, you skim ahead, you find what you're kind of looking for. Q. Question, that's just doing questions. It's active recall, I think they call it. The 3 R's. Fuck, what the fuck are the 3 R's? Space repetition is one of them, I think. The Feynman technique, I think, is one of those R's somehow. Teaching it to someone. Oh, I don't know. Anyways, let's get right on into this. This module provides an introduction to waves and interference. Alright. You'll complete the activities in this module in your student workbook. Download the workbook using the button below. Oh, I should probably do that. That's questions. Wait, why am I not doing questions? I should definitely do that. Let's download this workbook. I never download. Oh, it's because it's in fucking docs. Fuck's sakes. Always in docs, cunt. Alright, I'm gonna message my physics teacher again saying, "Hey sir, do you have the waves workbook in PDF?" To Joseph. Waves. Hey sir. Was wondering if you have a student workbook for waves in PDF form. Cards. And docs. Which doesn't work. Cheers. Berlin. Send. My package is in the country now. My dog leash. I want to make a store with that dog leash. Retractable dog leash, nylon foldable, travel bowl, portable puppy, water bottle, outdoor walking, running, traction rope, pet supplies. Let's go. It's in the country. Ooh. I got it from a dodgy ass brand. I don't know why. I don't know why I did that. Oh, that's a good picture. It's a really good picture. Have I got that picture downloaded? which is nice. Got a hook for the dog bags, got a leash, got a water bottle, got a bowl. It's got water, you can put water in it. It's like a canteen. There's a bowl, waste bags there, and a handle. It's gonna be fun on the bone. Come on, hopefully it arrives today. Why did I buy it at AliExpress, man? It's because I couldn't find it on Amazon. Plus it'd be way more expensive on Amazon. Rather just wait the 20 days for each packet shipping, you know what I'm saying? Okay. Enough getting distracted. You complete the activities in the model, blah blah blah. When I look through the question, mark your analysis using the answer guide. Waves are very common in nature and are very important to us. Animals and humans explore our environment through light and sound waves, correct? All of our communication devices such as cell phones, television sets and radios use waves. Waves are the most important means of transferring energy, including the energy from the sun to the earth. This lesson introduces the concepts and the terminology of wave motion. Let's watch this video. Let's go. There's a duck there. We're watching a video. This is
waves.
Awesome.
One of the first things we need to know about waves is there are two different types of wave.
Right. There is the standing wave. And then the interfering wave. I don't know why I'm thinking that. The fuck does it say?
One shown here by waves in the sea. And the other one shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second, and it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength. Or, to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learned these core concepts, it will give you much more confidence in the rest of the topic.
And in life in general. Alright. Cool. When you cup your hands, the air between your hands is compressed rapidly. Wave pulses. A wave pulse travels across the room. The air particles do not travel across the room at that time, but the energy does. Correct. A wave is a series of oscillations that travel through a medium. Okay, that's definitely important. I'm definitely going to jot that down. A wave. Seriously, my skin looks dog shit. What the fuck? A series of oscillations that travels through a medium. A medium. Just thinking about David Goggins, man, that guy is insane. That shit is crazy, the shit that he does, man. Just thinking, I don't even know why I popped into my head, but there's a story that he told on the Joe Rogan podcast where it's like, he had like this 100-mile race that he had to run. And, the day before that race, and he was like unprepared for it. The day before that race, the dude that he was trying to impress to get into the fucking Navy or the SEALs or whatever was there, and they like did this workout together. He was like, "Oh, come on, man, let's go for a workout." He knew that he was doing the 100-mile race the next day, and he was testing him. So he was like, "Come on, let's do a workout." So he did a workout, and his body got fucked from the workout. Like, they went really hard. The guy pushed him on the workout. And the next day he had a 100-mile race. And he did that race. And after that race he was like pissing blood, and it's like he was in a bathtub, just fucked. His body was fucked. But he did that race. I mean, he used to do like a marathon a day. He'd run like a marathon every single day. Just for no reason, just to stay fucking hard. That was his catchphrase. He said, "Stay hard." Wave is a series. An oscillation at the source of the wave causes particles in the medium to oscillate. Connections between the particles pass the oscillation from one particle to the next. The wave spreads or propagates. The central point from which each particle oscillates is called the equilibrium position. Okay. The displacement of a particle is its distance at any given moment from the equilibrium position. Oh, for fuck's sake, of course I'm writing that down as well. The displacement of a particle is its distance at any given moment from the equilibrium position. From the equilibrium position. Dude, that guy is biking fucking fast. Yeah. Repeated back and forth moment is... Go in, what the fuck? What is going on? Dude, I have no idea what the fuck is going on. Why can't I move these? Fucking, I guess I'm not doing that. Do I not have Wi-Fi? What the fuck? Alright, fucking, whatever. A boy bounces up and down on a trampoline. Awesome. He makes 8.0 back and forth movements in 28 seconds. Calculate the frequency and period of his oscillations. Boy bounces up and down on a trampoline. Awesome. Good for him. Makes 8 back and forth moments in 28 seconds. That's just F equals 1 over T. Now when that comes up. On his oscillations. Okay. 28 seconds. 8 divided by 28. That's T. 28 divided by 8. That's F. Right? Yeah. Hertz in your home. If you look for technical details about almost any electronic equipment, you'll find HC. Here are some examples. I don't give a fuck. Kilo, mega, giga. High frequencies are usually written with a prefix a bit before the main word to save writing lots of zeros. 1 kilohertz is 1,000 megahertz, it's 1,000,000 gigahertz, it's fucking 10 to the power 9. Choose the correct answers for the sensor curve. The number of back and forth vibrations in every second is called frequency and is measured in hertz. 24 crest passing. There are 24 wave crests passing a point in a lake in 5 minutes. The horizontal distance between the top of a crest and the bottom of a trough is 6 meters. That's my new phone, by the way. The phone case came. I don't know why I bought this phone case. I can't remember why. It's got this little thing. Look, I can leave it up against stuff. Look. Oh, it's dead. I was about to try the camera. I forgot. It's fucking dead. I'm not fast charging it because I'm not using it till I get that dog leash. And I can start using it for TikTok. And then just start using it in general. There are 24 wave crests passing a point in a lake in 5 minutes. 24 divided by 5 is the frequency. That would be 4.8. The horizontal distance, or 24 divided by 300 for it to be in seconds. I'm not fucked. The horizontal distance between the top of a crest and the bottom of the trough is 6 meters. Okay, the frequency all the way for this. Oh my god. Okay, 0.8. Yeah. Oh, for fuck's sakes. Fuck's sakes. Isn't it? 0.08. The fuck am I supposed to know the wavelength? Oh, there we go. Horizontal. Cool beans. A piece of driftwood is floating in the lake. The vertical distance between the lowest position of the driftwood and the highest position of the driftwood is 1.2 meters. The amplitude of the wave is 1.2 meters. I guess 0.6 meters. That's right, it's just in the middle of the wave. It's equilibrium. During high tide, water underwater rises 1.8 meters. The time between a low tide and a high tide is roughly 6 hours. Spirit of the thought is more than a feeling, more than a feeling. It's 12 hours. The amplitude of the tide is 0.9 meters. Radio station broadcast on a frequency of 516 kilohertz. There are 567,000 kilohertz. Hertz and kilohertz. The period of the wave is. What the fuck? I have to do 567 1, 2, 3 to the power of -1. 1, 7, oh for fuck, 1, 2, 3, 4, 5. There's 5 straight over here. Check answers. I got literally all of them right. Fuck me, I'm the man. Okay, moving on. Is the section gonna end soon? Oh, perfect, it'll end. And that time will be done. Then I'll start my 5-minute break, come back, do the 25 minutes last, and then this will be the end of the podcast, which was a pretty shitty podcast. But you guys be fucking grateful. Let's get right back on into it. Phase is a concept used to describe a particular moment in time. One complete oscillation around one horizon is numerous secondaries. 2 points are in a phase that are exactly in step with each other. are in phase if they move exactly in step with it. If they move exactly in step with each other. Awesome. Everything is awesome. Five, 4, 3, 2, 1. Okay. Yada yada yada. Okay, cool. Let's start my break. I'll be back in 5 minutes. Dude, that break goes on. Goes for quick. Don't you worry about it.
That she was completely asymptomatic and there was no reason for her whatsoever to suspect she had COVID. That's correct, John. And so I think people really need to get clear about that. So when they come to hospital, and we really want people to come to hospital if they need health care, so please don't stay away. We're open to more than 200 people. You will be screened. Please tell the truth so we can care for you and protect everyone. You'll still be seen and provided for you. But not everybody does.
Don't you worry about it. Oh, the screen froze. That sucks. Pardon me. Look at that. Okay, let's get back to work. Let's continue with waves. Yeah, next fucking lesson, pal. The fuck's going on there? Go to the next lesson. Yeah. Ooh, don't you worry about it. Most electronic communication, cell phone networks, radio and television use electromagnetic waves. Electromagnetic waves travel at the speed of light. What the fuck? That is 300 millimeters per second. That's pretty fucking quick. I can only run 200 mil. This is why text messages are delivered so fucking fast. This lesson looks at the characteristics of waves and how the speed of a wave relates to its frequency and its wavelength. Let's go. Mechanical waves. Mechanical waves are waves which propagate through a material medium. Solid, liquid, or gas. Okay. The speed of a wave in a medium depends on the elastic properties of the medium. Mechanical waves can be longitudinal waves or transverse. Alright. Yeah, that makes sense. And the wave, I wonder when the camera on my laptop stops on photo booth. Does that mean that the actual recording is like that, or just what I'm seeing? It never stops on a good frame either. Water drips into a bowl produces ripples or waves. The waves move horizontally, although the particles in the wave move approximately up and down. The speed of the ripple across the bowl is not the same as the speed of the water particles. The speed of a wave can be measured by timing a wave crest as it travels a fixed distance. Oh, oh, oh. Hey, yo. Ooh, don't you worry about it. The speed of the ripple across the is not the same as blah blah blah. V equals d over t, no shit. A wave in a pond travels 24 meters in 3 seconds. Okay, V equals d over t. Jesus Christ, man. Let's get to the fucking complicated shit, eh? No fucking V equals d over t. Watch the final video. Fucking love videos, alright? 5 minutes, let's go.
This is what a sound wave sounds like. But what does a sound wave look like? Well, the air through which the sound wave is traveling looks something like this. But if you want another visual representation of the sound, we can hook this speaker up to an oscilloscope and it gives us this graph. We say that this shape represents the sound wave because if we focus on a single molecule of air, we see that it moves back and forth just like a sine or cosine graph. The horizontal axis here represents time, and the vertical axis can be thought of as representing the displacement of that air molecule as it oscillates back and forth. The center line here represents the equilibrium position or undisturbed position of that air molecule. If we turn up the volume, we see that the oscillations become larger and the sound becomes louder. The maximum displacement of the air molecule from its undisturbed position is called the amplitude. Be careful, the amplitude is not the length of the entire displacement. It's only the maximum displacement measured from the equilibrium position. Another key idea is the period of a sound wave. The period is defined to be the time it takes for an air molecule to fully move back and forth one time. We call this back and forth motion a cycle. We measure the period in seconds, so the period is the number of seconds it takes for one cycle. We use the letter capital T to represent the period. If we decrease the period, the time it takes for the air molecules to oscillate back and forth decreases, and the note or the pitch of the sound changes. The less time it takes the air molecules to oscillate back and forth, the higher note that we perceive. An idea intimately related to the period is called the frequency. Frequency is defined to be 1 over the period. So since the period is the number of seconds per oscillation, the frequency is the number of oscillations per second. Frequency has units of 1 over seconds, and we call 1 over a second a hertz. Typical sounds have frequencies in the hundreds or even thousands of hertz. For instance, this note, which is an A note, is causing air to oscillate back and forth 440 times per second, so the frequency of this A note is 440 hertz. Higher notes have higher frequencies, and lower notes have lower frequencies. Humans can hear frequencies as low as about 20 hertz, and as high as about 20,000 hertz. But if a speaker were to oscillate air back and forth more than about 20,000 times per second, it would create sound waves, but we wouldn't be able to hear them. For instance, this speaker is still playing a note, but we can't hear it right now. Dogs could hear this note though. Dogs can hear frequencies up to at least 40,000 hertz. Another key idea in sound waves is the wavelength of the sound wave. The idea of a wavelength is that when this sound is traveling through a region of air, the air molecules will be compressed close together in some regions and spread far apart from each other in other regions. If you find the distance between two compressed regions, that would be the wavelength of that sound wave. Since the wavelength is a distance, we measure it in meters. Be careful, people get wavelength and period mixed up all the time. The period of a sound wave is the time it takes for an air molecule to oscillate back and forth one time. The wavelength of a sound wave is the distance between two compressed regions of air. People get these mixed up because there's an alternate way to create a graph of...
Okay, what the fuck? I've never heard that before. Wavelength. Distance between groups of compressed air. I've never heard that compressed air shit. It's a pretty nice day today.
this sound wave. Consider this: before the wave moves through the air, each air molecule has some undisturbed position from the speaker that we can measure in meters. This number represents the equilibrium undisturbed position of that air molecule. Then, as the sound wave passes by, the air molecules get displaced slightly from that position. So an alternate graph that we could make would be the displacement of the air molecule versus the undisturbed position or equilibrium position of that air molecule. This graph would let us know for a particular moment in time how displaced is that air molecule at that particular position in space. This graph shows us that in some regions the air is displaced a lot from its equilibrium position, and in other regions the air is not displaced much at all from its equilibrium position. For this kind of graph, the distance between peaks represents the wavelength of the sound wave, not the period, because it would be measuring the distance between compressed regions in space. So be careful. For a sound wave, a displacement versus time graph represents what that particular air molecule is doing as a function of time. And on this type of graph, the interval between peaks represents the period of the wave. But a displacement versus position graph represents a snapshot of the displacement of all the air molecules along that wave at a particular instant of time. And on this type of graph, the interval between peaks represents the wavelength.
Oh, I tuned out there for some reason. Right, let's go back
Wave. Consider this: before the wave moves through the air, each air molecule has some undisturbed position from the speaker that we can measure in meters. This number represents the equilibrium undisturbed position of that air molecule. Then, as the sound wave passes by, the air molecules get displaced slightly from that position. So an alternate graph that we could make would be the displacement of the air molecule versus the undisturbed position or equilibrium position of that air molecule. This graph would let us know for a particular moment in time how displaced is that air molecule at that particular position in space. This graph shows us that in some regions the air is displaced a lot from its equilibrium position, and in other regions the air is not displaced much at all from its equilibrium position. For this kind of graph, the distance between peaks represents the wavelength of the sound wave, not the period, because it would be measuring the distance between compressed regions in space. So be careful. For a sound wave, a displacement versus time graph represents what that particular air molecule is doing as a function of time. And on this type of graph, the interval between peaks represents the period of the wave. But a displacement versus position graph represents a snapshot of the displacement of all the air molecules along that wave at a particular instant of time. And on this type of graph, the interval between peaks represents the wavelength.
Awesome. Everything is awesome. Got the camera back. Everything is awesome. Remember that song, Flynn? From that fucking Lego movie? Everything is awesome. Everything is cool when you're part of a team. Everything is awesome when you're living in a dream. Sound waves are longitudinal waves, pretty sure. Increasing frequency makes it higher pitched. Cool. Yes, another video. I love videos where I just sit back and relax.
The electromagnetic spectrum.
See how Oh yeah, I'll just finish this. Cool, awesome.
Light is actually an electromagnetic wave and is part of a whole spectrum of waves called the electromagnetic spectrum. The waves all have certain things in common. They all travel at the speed of light in a vacuum, and they can all be reflected, refracted, and diffracted. So, how are the different parts different? Well, it's the frequency and the wavelength that change. So, here on the screen is the electromagnetic spectrum. We have radio waves on the left. They have the longest wavelength and the lowest frequency. And as we move from left to right, the wavelength decreases and the frequency increases. Also, the energy the wave carries increases as well. Now, next to radio waves is microwaves. Then we have infrared, followed by visible light, which is right bang in the middle of the spectrum. Then we have the high energy side with ultraviolet, X-rays, and finally gamma rays. You need to memorize this spectrum and know how the wavelength and frequency change as you move along it. Okay, let's look some more at the lower energy half of the spectrum, from radio waves up to visible light. All these parts of the spectrum are used in communications. Radio waves are used for sending TV and radio signals, both short and long distances. Really short wavelengths are used for very short distances, and the longer wavelength for longer distances, as they can reflect off a layer of charged particles in the atmosphere called the ionosphere. However, radio waves can't pass through the ionosphere, so if we want to communicate with satellites, we must use microwaves, as they will easily pass through the ionosphere. Microwaves are also used in mobile phones, and certain wavelengths are absorbed strongly by water molecules and so are used to cook food. These are not the wavelengths, however, that are used in mobile phones. Infrared, as we know, carries heat and can be used in...
I keep on seeing fucking people going to school. Those fucks have to go to school now. That is fucking hilarious. So that could be a year 12. Huh. Or year 11.
thermal imaging.
It's my neighbour. The neighbour kid doesn't like me. I remember I used to do a we each used to do a little circular delivery run. Oh, there's my dog. I'll show you my dog. Here she is. Can you see her? She's sniffing shit. She is sniffing shit. Me and that kid next door, we used to do a delivery run with each other, and I used to have a bike, and I don't even remember what happened, but back in the day, you know, you'd have back in the day, I guess me and a lot of people still, one encounter where things don't go really right, then they just fucking, okay, that person, we never talk to each other again. We fucking hate each other now. So I biked past him and remember saying something to him and he just didn't say anything back. I just kept on biking. Then we each decided to hate each other.
Imaging and for grills for cooking, and it is also used in communications, as is visible light, both being sent down optical fibres. So all these four lower energy electromagnetic waves are used in communication. But is there any danger in using them? Well, at the moment, there is no scientific evidence that any of these parts of the EM spectrum pose any danger whatsoever.
Awesome.
Apart from maybe getting burnt by infrared. Now let's move on to look at the high energy part of the spectrum. Okay. So what are these used for? Well, ultraviolet is used in sunbeds to help you get a suntan. And it's also used in special security inks because they absorb ultraviolet and emit visible light. X-rays, obviously, are used to look for broken bones in hospitals. And finally, gamma rays are used to kill bacteria in food, to keep it fresh longer, to sterilize surgical equipment, and also to kill cancer cells in radiotherapy.
Let's go.
Now, this is the high energy part of the spectrum, so there are dangers with using these.
Yeah.
As you know, too much exposure to ultraviolet can cause skin cancer. Now, X-rays and gamma rays are even more dangerous, as they have enough energy to remove an electron from an atom, creating an ion. We call this ionization. And this can really damage cells and can actually kill them or cause mutations in them, leading to cancer. So exposure to high doses of X-rays and gamma rays really needs to be minimized. It's okay when you're just going for 1 or 2 X-rays at the hospital, but it's why the people working in the hospitals need to take extra precautions to minimize their dose. And that is the EM spectrum. Make sure you learn the entire electromagnetic spectrum and the uses and dangers of each part.
Okay. When you listen to the radio, watch television, or cook dinner in a microwave oven, use electromagnetic waves. That is part of a series called the electromagnetic spectrum. The electromagnetic waves are transverse in radio circuits that are produced by the oscillation of electrically charged particles. And like all of the waves, they do not require a medium to travel through. They can travel through empty space as well as through air and other substances. Awesome. In a vacuum, all types of electromagnetic waves travel at the same speed, the speed of light. Because air slows the waves down very little, the speed of electromagnetic radiation in air is also the speed. Because air slows the waves down very little. Okay. Electromagnetic waves come in a huge range of sizes. And one in the spectrum of radio waves, which have a very low frequency and low wavelength. At the other end of the spectrum are high frequency gamma rays. Visible light is a small part of the spectrum. Red light has the longest visible wavelength. Violet has the shortest. Wave velocity depends on the medium through which the wave is travelling. If the medium does not change, the wave velocity does not change. The wave frequency depends on the frequency of the wave source. The frequency cannot change once the wave is the source. Okay, let's jot that down. Once the wave is the source. It's a beautiful day and I can... If the frequency is increased, more waves are produced per second. Because the velocity of the waves doesn't change, the wavelength decreases. You often need to round numbers in your answer to a problem to ensure that you do not give your answer to a higher level of accuracy than the data was used in the problem. To avoid increased error in the calculation, it is best not to round until you have a final answer. In the example above, the data is given to fucking no shit. In transverse way, I'm really bad at reading. In transverse wave motion, the particles of the medium vibrate at right angles, the direction in which the wave travels. In a longitudinal wave, the particle vibrates parallel to the direction of wave motion. Velocity v is the distance traveled by a wave front per second. The velocity of a wave depends on the type of wave the medium travels through. The speed of the wave remains the same as the medium changes. The speed is v equals f Landau. Okay. Awesome. Alright, that's the motherfucking podcast. Let's quit out of that. Scoot. and let's end the podcast. See ya.